Okay, then let's move on. In the last class, we started looking at multi-electron atoms and how electrons fill into multi-electron atoms. And we have seen that, well, we cannot solve the Schrödinger equation anymore exactly, so we have to work with approximations. And one very simple but a pretty good way to estimate electron energies in orbitals of multi-electron atoms are the Slater rules. So with the help of the Slater rules, we calculate a shielding constant from which we calculate an effective nuclear charge. And with the help of the effective nuclear charge, we can then calculate the energy of the electrons in the orbitals, which can help us to determine, well, what is the electron configuration of our atom in the ground state. And we have done one example in the last class. That was the potassium. I wanted to add one more example, which is a little bit more complex, which is the iron atom. And I just need to wait here for the screen. Okay. So for the iron atom, again, we can think of different electron configurations in the ground state. So for example, we think of the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So it would fill the 4s subshell before we actually fill the 3d subshell. Or another possibility is that the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d8, 4s0. In this case, the 3d subshell would be filled before the 4s subshell. So can the Slater rules actually have to decide what's the electron configuration in the ground state? This example is a bit more complex than the previous one because we have to consider overall 8 electrons. Okay. The other electrons we do not need to consider because they are in the same orbitals. Okay, so of course they will have the same energy, but the last 8 are the deciding ones. So let us look at this electron configuration here first, with the 4s subshell being filled first. We need to first write out the electron configuration in Slater form. And that means that we have to list the 3d orbitals first, the 3d electrons first, and then the 4s orbitals. And we have to place parentheses around the electrons which have approximately the same energy. So always the s and the p orbitals of the same quantum m, they're getting grouped together. All other orbitals are their own group. So now we have to calculate the energies for all these electrons. So in the first step, we need to determine the shielding constant effective nuclear charge for these electrons. Okay, so we can, for instance, start with these 3d electrons first and determine the shielding constant. We actually find that, well, these 2 electrons here to the right don't count because they are further away. So we have 5 additional electrons in addition to the d electron that we're actually looking at. And because these are in the same group, they account for 0.35 each. Okay, we have 5 times 0.35, and then we have 18 times 1.0. That is because we're looking at the d electron. So any other electrons which are to the left of the electron in the group that we are looking at, they count with a factor of 1.0, so all 18, so these are 18. So we have 18 times 1, okay, added to 5 times 0.35, and that gives 19.75. Okay, so in the next step, we can calculate the effective nuclear charge for such a d electron, and that's the real nuclear charge, which in this case 26, because our iron has 26 protons, minus 19.75, that's the value we just calculated here, and that's 6.25. Okay, so we have to calculate now the same for the 4s electrons. So if we put ourselves on a 4s electron, then there is one other electron in the same group, the other 4s electron. So we have 1 times 0.35, okay, that one electron shields with a factor of 0.35. And then we have 14 electrons that shield with a factor of 0.85. So these are those that are in the n-1 shell, which is in this case the third shell. Yeah. So we have 2 plus 6 plus 6 is overall 14 electrons. And then the remaining electrons, these are these 10 here. They fully shield because they're in an n-2 shell. And if we sum this up, then this gives a value of 22.25. Okay, so what is the effective nuclear charge acting on a 4s electron? Well, that's 26 minus 22.25, which is equal to 3.75. Okay, so now we can calculate the energies of these electrons the following way. For a 3d electron, and we for now consider only one, the energy is the effective nuclear charge square over n square times 13.6 electron volts. So this is 6.25 square, okay, so this is this value here, over 3 square. That's because we are looking at an electron in the third shell, a 3d electron in this case, times 13.6 electron volts, and that's minus 59.03 electron volts. So now we have to consider that we have overall 6 of these d electrons. Okay, so therefore the overall energy for all the 6 d electrons is 6 times minus 59.03 electron volts, which is equal to minus 354.17 electron volts. So we have to do an analogous calculation for the s electrons. So for one 4s electron, the energy is the effective nuclear charge square, which is 3.75 in this case, over 4 square, because n is equal to 4, times 13.6 electron volts, and that's minus 11.95 electron volts. So we have to consider that we have overall 2 of these electrons, okay? So both 4s electrons then have an overall energy of 2 times minus 11.95 electron volts, which is 23.90 electron volts. So now we can add also all the 6 electrons together, the d electrons and the s electrons. So that would then be minus 354.17 volts minus 23.90 electron volts, which gives minus 378.1 electron volt. So now we are finished with our first electron configuration. Let's go to our second electron configuration. So in Slater form, this electron configuration runs like this. So we place now the 3d electrons in front of the 4s electrons. Again, so but in contrast to the previous case, we have 8d electrons and 0 4s electrons. So now, what are the the shielding constants, well, that is 7 times 0.35. Why? Because we have 7 other electrons in the group of the 3D electrons. Okay, never count the electron that we're actually looking at. And we add to that all the other electrons below to the left of that group, and they fully shield, so they get a factor of 1.0, and overall these are 18. So we add 18 to 7 times 0.35, and that's 20.45. So now we can calculate the effective nuclear charge on a 3D electron, which is now 26 minus 20.45, which is equal to 5.55. So with that, we can calculate the energy of the electrons, and we directly consider all the 8 electrons. So we have 5.55 square over 3 square times 30.6 electron volts times 8. Of course, we should not forget the minus sign, indicating that this is a binding energy, and this is then minus 372.3 electron volts. So we see that this value here is lower than that value over there, which means that, well, this electron configuration 4s2 3d6 is the ground state electron configuration, and not this electron configuration here. Okay, so this is in accordance with what we experimentally observed. So again, we see that the Slater rules, by very simple means, can calculate orbital energies and predict electron configurations. Okay, so there's, however, one other factor that needs to be considered when fully accounting for orbital energy. So thus far, we have only considered electrostatic interactions. So shielding effects are nothing else but electrostatic forces, or they account for electrostatic forces. However, there are also magnetic forces, because the electron has a spin, and therefore there is a magnetic momentum associated with that spin. So the electrons behave like the rod magnets that are interact. Okay, the magnetic fields of these little magnetic rods, they interact. Okay, and they can interact, well, either more favorably or less favorably, depending on how the spins are being oriented, and that, of course, also reflects the orbital energies. So how can we predict which, well, spin configurations are actually lowering orbital energies overall? And that is reflected by Hund's rule of maximum multiplicity, named after Friedrich Hund, which says that the electrons of a subshell are filled so that the number of electrons with the same spin gets maximized. Okay, so electron configuration with the maximum number of unpaired electrons, they interact most favorably with each other, lowering the energy of the electron configuration. Now, when you compare the 2 electron configurations that we discussed thus far, or discussed just now, then you see that in the electron configuration 4s2 3d6, we have 4 unpaired electrons, while in the electron configuration 4s0 3d8, we have only 2 unpaired electrons. Okay, and that means that the first electron configuration is not only favorable, favored because of electrostatic interactions, but also because of magnetic interactions. Okay, but this is not accounted for by the Slater rules, because the Slater rules only account for electrostatic interactions. But in some cases, the magnetic interactions can also be important. We will go to that. In a moment. All right, so now we have basically considered everything that we need to explain ground state electron configurations, which explain the Aufbau principle of multi-electron atoms. Okay, so we can just go through the atoms one by one. We can start with the hydrogen. Of course, our only electron in the hydrogen would be in the 1s orbital. Okay, as we go from hydrogen to the helium, we can still fill the second electron in the 1s orbital, but we have to fill it in with opposite spin because of the Pauli principle. So for the lithium, we must start a new shell. We have to fill the 2s orbital halfways. That is again because of the Pauli principle. We cannot fill the third electron into the 1s orbital anymore. So now for the beryllium, we would pair our electron in the 2s orbital, making the 2s subshell full. So for the boron, we have to again start a new subshell because of the Pauli principle. Okay. And now as we go from the boron to the carbon, we have to start considering Hund's rule, right? Because the additional electron in the carbon could now be, well, filled, well, into the same orbital, whereby the electron would be spin down, but it could also be filled into a different orbital, and it could be filled into a different orbital, either spin up or spin down. So Hund's rule says we have to fill the electrons into different orbitals with both spin up. Okay. Now, the same you have to consider also then for the nitrogen. So the additional electron for the nitrogen then needs to be filled into the third p orbital, and again the spin has to be up to maximize the number of unpaired spins. As we go from nitrogen to the oxygen, we have to start pairing the spins. There's no other possibility. We have to pair two spins as we go from oxygen to the fluorine. And all the spins are then paired as we go from the fluorine to the neon. And with the neon, we have then the second shell completely full. We have reached the so-called noble gas electron configuration. Okay, all the entire shell is completely full. So now as we go from neon to the potassium, we have to start a new shell. Okay, so we have to fill the 3s orbital halfways. We go from sodium to the magnesium. Our 3s orbital will be completely full. If we go from magnesium to aluminum, we have to start the 3p subshell. And then again, we have to fill more electrons according to Hund's rule. So for the silicon, again, we have to fill the additional electron into a different p orbital, and we have to fill it in with a spin up. So again, Hund's rule applies. Hund's rule applies also when we go from silicon to the phosphorus. After that, we need to start pairing the spins. So for the sulfur, one p orbital would be completely full. For the chlorine, 2 p orbitals would be completely full with paired electrons. And for the argon, then all of them will be filled, and our third shell is completely full, and we have again achieved the noble gas electron configuration. Okay, then if we go further, we go from the argon to the potassium, and for the potassium, we would now have basically the choice: do we fill the 3D subshell or the 4s subshell? We have just seen with the Slater rule, we can predict that the 4s subshell is being filled, okay, because that gives the electron configuration with a lower energy. Okay, so 4s before 3d. So that also means, that also applies to the calcium. So for the calcium, the 4s subshell is being filled. Okay. Only as we go from the calcium to the scandium, we start filling the 3d subshell. And again, we do this under consideration of Hund's rule. Okay. So as we go from scandium to the titanium, well, our additional electron would go into a different d orbital with the same, having the same spin. As we go from titanium to vanadium, we would have 3 unpaired electrons in 3 different d orbitals. As we go from the vanadium to the chromium, however, we see an exception. Okay, which we again can explain by the interaction of the magnetic fields associated with the spin of the electron. So instead of an electron configuration 4s2 3d4, we're actually getting an electron configuration 4s1 3d5. And that is because you see that in this case, we have a half-filled 3d subshell in which all electrons have the same spin, which is energetically quite favorable. In addition, we have another unpaired electron in the 4s. Okay, so because of the magnetic interaction in the chromium, the 3d5 4s1 electron configuration is favored over the 3d4 4s2 electron configuration. So this is an exception that you should keep in mind. So now as we go from chromium to manganese, everything is normal again. So for the manganese, we have a half-filled 3d subshell and a completely filled 4s subshell. As we go from manganese to the iron, we have to start pairing the spins in the 3d subshell. For the iron, we have one 3d orbital being completely full. For the cobalt, it's 2. For the nickel, it's 3. And for the copper, again, we have another exception. So instead of the expected electron configuration 4s2 3d9, we observe the electron configuration 4s1 3d10. And that is because a full d subshell is also a particularly stable electron configuration. It's actually more stable than a full s subshell. And therefore, our electron moves in this case from the 4s to the 3d subshell in order to make the 3d subshell complete. So for the zinc, we then have all 3d and all 4s orbitals being completely full. So as we go from the zinc to the gallium, we then have to start a p subshell. Okay, that would be then the 4p subshell. And again, we would fill the p subshell according to Hund's rule. For gallium, we would have 1 unpaired electron. For germanium, we would have 2. For arsenic, we would have 3. And after that, we would start to pair the spins again. So for the selenium, we would have 1 set of paired electrons. For the bromine, we would have 2. And for the krypton, then all p orbitals would be filled. We would have filled now the entire fourth shell, okay, which would again represent the noble gas electron configuration. Okay, so now we could continue that, but there's not then a lot new to learn. So I'm stopping here, but of course there are more electrons with more electron configurations to consider. So now with the help of the quantum mechanical model of the electron, we can very nicely now explain the periodic table of the element. So the periodic table of the element was actually invented long before the quantum mechanical model of the atom was developed, but one could not explain the periodic table of the element very well. But with the help or with the knowledge about the quantum mechanical model of the atom, the periodic table could be nicely explained. Okay, so originally in the periodic table, the atoms were arranged by mass. Okay, so one would just make a row of elements with increasing mass. So from the left to the right, the mass would increase, but whenever one would find an element that had similar property than an element already encountered before, then a new period would be started. And that would give a table of periods and of rows and columns, periods and groups, as we would call it today. But there wasn't a good explanation as to, well, why do certain elements have similar properties than other elements, and the quantum mechanical model of the atom nicely explains this. Okay, it explains this by the number of electrons, by the number of valence electrons in a particular electron configuration of an atom. So, for instance, when you look at all the elements in the first group here, then they all have in common that they have one s electron as the valence electron. So a valence electron, as you probably all remember, is an electron that is in the outmost shell of the atom, and because of that, it determines its chemical and physical properties, because these electrons are most reactive because they have the highest energy. Okay, the type and the number of the valence electrons essentially determines the chemical behavior, and therefore, when an element has the same number on type of valence electron, the same valence electron configuration, then it has similar properties, and for that reason, these elements are in the same group. So in the first group, we will find only elements that have one s electron as the valence electron. Okay, for the hydrogen, it's the 1s. For the lithium, it's the 2s electron. For the sodium, it's 3s electron, and so forth. For the second group, the elements would have 2 s valence electrons. Okay, so for the next 10 groups here, okay, the elements would have not only s valence electrons, but in addition to that, also d valence electrons. And the number of the d valence electrons would increase from the left to the right. Okay, so the first two groups here, because they have only s valence electrons, are called the s block. So those elements that also have d valence electrons are called the d block. Okay, so now here to the right, you see all the elements that have also p valence electrons. So s and p valence electrons, and this is then called the p block. Okay, so for this group here, this is the 13th group, we have 1 p valence electron. Here for the 14th group, we have 2, and for the 15th group, we have 3. For the 16th group, we have 4. For the 17th group, we have 5. And here in the last group, in the 18th group, we have 6, okay, with the exception of the helium. So the helium has the electron configuration 1s2. So because of that, one could also put it here above the beryllium, but that's not conventionally done so because the helium has properties which are much more similar to the other noble gases, okay, in comparison to the earth alkaline metals, and that's because in the first shell we achieve a 4 shell without needing any p electrons because we cannot have p orbitals. Okay, therefore, just a 4-1s shell represents all the noble gas electron configuration, and that's why the helium behaves this way, and this justifies its position in the 18th group and not in the second group. Okay, so with the help of the quantum mechanical model, we can explain why we actually have 18 groups in the periodic table. Okay, but we can also explain why we actually have overall 7 periods. So whenever we start a new period, well, then we start filling a new shell with electrons. Okay, so as we go from the first period to the second period, we start to fill the second shells, start filling orbitals with the quantum number n is equal to 2. As we go from the second shell to the third shell, we will start filling orbitals with the quantum number n equal to 3. In the fourth period, we will then start filling orbitals with a quantum number n equal to 4, and so forth. Okay. Now you see here, in addition to all these elements that we have discussed, there are also these here, and that's called the so-called F block. So the F block actually doesn't get a group number, okay, because otherwise, and it's typically not inserted here in between the S block and the D block, because otherwise the periodic table would just get too wide. Instead, this F block is actually usually placed here underneath the periodic table. So the F block is containing the so-called lanthanides and the actinides. The lanthanides are the elements here in the first period. So that's overall the fifth period. No, sorry. No, it's actually the sixth period, not the fifth. And these elements are called the actinides, so they are on the 7th period of the periodic table. So you see that these blocks start with the elements lanthanum for the lanthanides and actinium for the actinides. So I'd like to point out that the lanthanum and the actinium themselves are not elements that have F electrons. Okay, the lanthanum and the actinium are actually located in the periodic table below the yttrium. Okay, and the F block elements are only those that follow the lanthanum and the actinium respectively. Okay, so these are actually just these. So please keep that in mind. So lanthanum is actually a group 3 element, and actinium as well. Okay, so lanthanide actually comes from the Greek, the elements following the lanthanide. Okay, but the lanthanum itself doesn't belong to the lanthanides. Okay, so the periodic table is basically the alphabet of the inorganic chemists. So therefore, in this class, I would like you to know all the elements, the element symbols, and also their position in the periodic table. So that is a little bit of a memorization effort. Memorization is mostly not the most interesting thing to do, but it can be made easier and more fun and entertaining. And because of that, I actually wanted to show you a brief video about a song of the periodic table that I think can actually help you to memorize the periodic table. So let's just listen to it.
There's antimony, arsenic.
Oops, I didn't want it.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
Okay, so what I would like to know from you is actually the first 86 elements in the periodic table. Okay, so the periodic table has more than that, but everything which actually is beyond 86 is mostly radioactive. Okay, so basically that would include here the lanthanides, okay, as well as here this P block up to the element radon, yeah? But it would not include here the actinides, and it would also not include the elements 104 to 118, all of which are actually radioactive and have a very short half-life time. So I just wanted to mention here that here's the last 5. They're actually just very recently added a couple of years ago. And they now actually make the 7th period complete. Okay, so now we have all 7 periods completed with known elements, and we can wait until the first element in the 8th period will be discovered. See how stable it is. Okay, then on the next step, let us look more closely at what is called the periodic properties of the elements. So generally, a periodic property is a property of an element on atom that, well, changes systematically due to its position in the periodic table. Okay? So the first property that we would like to look at here is the atomic radius. So here, see here the atomic radii of the elements. So let us see, well, can we actually see trends associated with atomic radii? Can we see in which way the atomic radius is influenced by the position of the atom within the periodic table? Okay, so for instance, we can go within a period from the left to the right and see if we see a trend according to which the atomic radius of the atom changes. Okay, so now for the first period, we'd see, well, the helium is smaller than the hydrogen. For the second period, we would see that the atomic radius continuously declines to go from the left to the right. And the same is also true for the third period and also all the other periods. So that constitutes the first trend, which says that the atomic radii of atoms decrease within a period with increasing atomic number. Now, the question is, how can we explain this? And can we explain this with a quantum mechanical model of the atom that we have just developed? And the answer is we can when we consider the following. So as we go from the left to the right within the period, we add, well, electrons, but at the same time, we also add the same number of protons. Okay. So now, therefore, because we increase the number of protons, the force by which the electrons are being attracted increases the electrostatic force. And that tends to contract the atom, okay? Because the electrons are drawn closer to the nucleus. But on the other hand, because we have more electrons, we also have increased electron repulsion. And that tends to, well, increase the size of the atom. Okay. Now, the first effect is larger than the second effect, because of which overall the atomic size decreases. And we can explain why the first effect is larger, because we add the electrons within a period to the same shell. Okay, so for that reason, the electrons underneath cannot shield away the additional nuclear charge very effectively, and for that reason, overall the effective nuclear charge increases, which leads to a contraction of the atoms. So that explains the first trend. So atomic radius decreases continuously within a period. So then there's a second trend, which says that the atomic radius jumps when a new period is begun. So for instance, as we go from the helium to the sodium, we see a big jump. As we go from the neon to the potassium, again, we see a big jump. So how can we explain this big jump? Well, we start a new period. So that means that we need to fill a new shell, and that new shell is just much further away from the nucleus. Okay, so we're adding now an electron to a new shell, and that electron is naturally much further away from the nucleus. And then we have a third trend, which says that the atomic radius increases down a groove. Basically, this third trend can be understood as the sum of the first two trends. So in a period, we get a decline of atomic radius, but it's gradual and not all that strong. But because we always get this big jump as we start a new period. Okay? Overall, as we go from down a group, our radius increases. You can also understand this a different way within within a group. We have the same valence electron configuration, but the quantum number n increases, and as the quantum number n increases, the electrons are, of course, further away from the nucleus. Okay, then let's look at another. When talking about atomic radii, one always needs to say which concept of atomic radius you actually want to use, because there are different definitions. It's actually not so easy to define atomic radius. So, for instance, we could define an atomic radius as the distance between two atoms in a homoleptic molecule like Cl2. Okay, so the radius would be defined by half of the distance between the two chlorine atoms in this Cl2 molecule. Okay, that would be one useful definition, and that is the so-called covalent atomic radius, or the covalent radius. But one could also use a different definition, which is called van der Waals radius. One could also say, well, when we have a chlorine in solid state, okay, then we have also chlorine atoms next to each other, which are not bonded to each other, which belong to different Cl2 molecules. Okay, and we define the atomic radius as half of the distance between these atoms. Okay, that would be another way to define it. We would call this atomic radius then the so-called van der Waals radius, because there are only weak van der Waals interactions between the two atoms in question. Okay, or van der Waals forces between two Cl2 molecules. In some instances, you can only define a van der Waals radius. So, for instance, when you look at argon, right? You could define a van der Waals radius in solid argon. But in solid argon, you, of course, you only have, you don't have molecules, you have only single atoms where van der Waals forces exist in between. Of course, you have to cool the argon to a very low temperature to make it solid. But you can then look at, well, what's the difference between the atoms? And naturally, that would define a van der Waals radius, but you could not give a covalent radius for an argon atom, just because argon molecules simply do not exist. Okay. So lastly, you can also define a metallic radius. That would then, however, apply only to metals, in which you would define the radius halfway as half of the distance between two atoms within the metal. Okay, so when you talk about atomic radius, you always need to say which definition of atomic radius you use, so that you are not compare apples and oranges. So last but not least, there's also a computational definition of the atomic radius. Okay, so you can also, well, compute orbitals associated with orbital sizes, and it's learned before. The orbital size is defined as the volume in which the probability to find the electron is 90%. Okay, so the same you can also do with an atom. Okay, so you can calculate on a computer the volume in which the electron density or the probability to find the electron, or probability to find the electron is 90%, which then defines the size of the atom. So in this case, you would look at an individual atom, yeah, without considering any neighbors, but can do this practically only on a computer. So this kind of atomic radius is actually being used here in this graph. Okay, so I see our time is over. So let us stop here. Don't forget to read the textbook. Also, don't forget to do the associate homework questions. Otherwise, let's just